Alright, next let's look at this problem here. So it's actually, well, the same thing, but alright, so here it's still a searching problem, but what we have here now is, aside from yung values, we also have corresponding other stuff with those values. So you can think of it as keys and values. So here you have the keys, and here you have key value pairs. So what you want is, this is kind of like yung lookup problem when we introduce dictionaries. For each query here, you look at if this list here contains an entry where the key is equal to that query. If so, you return the value. Otherwise, you return none. So obviously, as I just mentioned, you can use dictionaries for this. But can we do it without dictionaries? And actually, you can. Well, of course, you can just brute force this. But to do it quickly, you have to do something first. So a hint for that is sorting. So by sorting this input over here, if you sort the input for each query here, you can quickly find the corresponding value for this key. So yeah, that is how you would solve this problem here. So you might ask, why should we use a dictionary? Or why shouldn't we use a dictionary? So yeah, that is kind of true. Of course, if a dictionary already exists, there's nothing stopping us from just using it. But that only applies for this particular problem, for this problem over here. So if the problem was slightly different, let's say this is some query, and we want the smallest key, that's at least k, then using a dictionary would no longer work, since dictionaries don't really support this idea over here, getting the smallest key greater than or equal to some value. So because you can't use a dictionary, you have to use something else. And in fact, yung suggested solution for this, the one without a dictionary, is also going to work for this slightly different problem over here. So yeah, if you want to try that out, feel free to do so. Again, the main idea if for this alternate problem is still the same. Try to sort the input and do something on that input. Okay, so there. The main point that we want to go over here isn't the fact that you can solve this using sorting. We've seen many problems involving Sano search at this point. What I want to look at now is this key assumption that we're making. This one. This line over here. Sorting is fast. So why is that the case? Why is sorting fast? Well, to look at that, let's try to sort our subs. So again, sorting is, you have some sequence and you arrange that sequence in increasing order. So this is the problem that sorting is trying to solve. So if you have this input, you expect this output over here. Okay, of course, we all know, hopefully, that there are built-in functions for this. But how do we actually implement that function? How did Python implement this sorted function? Okay, so we're going to assume that we don't have these available to us, so we have to implement it ourselves. Alright, so the first thing that we can try to do is, well, take this definition literally. We want the values in increasing order. So how do we do that? Well, one thing we can do is use wishful thinking. So again, you have some sequence. You split that to the first element and the rest of the elements. So yung first element, or this is not necessarily yung first element ng sequence. This could be something else. Here, that's the smallest element, since you want the smallest element in front, like here. So you take the smallest element and you put that in front, of course, since you want to sort it. And what you do with the rest of the sequence is you use wishful thinking in order to sort the rest. So, of course, the most straightforward way to do this is using recursion. So if you try to do that, this is actually going to be slow. Why is this slow? Let's try to look here. So here let's say we have 3, 1, 2, 4 or 4, 2. This is our sequence. What we're doing here is we're taking the smallest element, so that's 1, and we are adding that onto whatever the result is from calling sorted on 3, 4, 2. This is what we're basically doing. So first things first, to get the smallest element, this already takes n steps. So getting the 1 out of 3, 1, 4, 2, this already takes O of n time. And same thing for this recursive call. If we look at what's happening here, this takes the smallest element here, so 1 plus, I'll put brackets here. So this is 3 plus 4 and 2, or sorted of 4 and 2. Again, to look for this 3, you have to go through this entire subarray. And same thing for the recursive call here. So what that means is you have to do n plus n minus 1 plus so on until you reach the very end. So all of this corresponds to this number of steps, which is, if you sum all of that up, this takes O of n squared steps. Okay, so that's pretty slow, as we've just seen from the first part of this lecture. Okay, so this kind of sorting, where we select an element and we put it in front, then we recursively sort the rest of the elements, this is what we call selection sort. So you're selecting the element to put in front, and you sort the rest of the elements. So this selection sort, this is also kind of how you would sort, say, playing cards. So if you're given a hand of cards, you take the smallest one, put it in your leftmost, or put it as the leftmost card of your hand, then you sort the remaining elements, something like that. So that's selection sort, and selection sort is quadratic, so it's pretty slow. Okay, so an algorithm here, which we've already briefly went over in the previous lectures. Again, this is a series of instructions that solves a particular problem. So here, this selection sort, this is an algorithm that we can use for the sorting problem. Okay, what's another thing that we can do? Well, what if we try to do kind of the reverse? For selection sort, we looked at what to consider for the first element. Here, what we're going to do is at each step, we're going to sort the first several elements, then put the last element where it's supposed to be. So this is also how you could possibly sort cards with your hands. And for that, just like yung previous example, you can do it with either recursion or with loops. So, okay. So here, the sorting of the n-1 elements, let's say you have this example here, 3, 1, 4, 2. What you're doing here is you sort 3, 1, and 4 first, so that's 1, 3, and 4. Then you decide where to put the number 2. So this decision of where to put the number 2, this is the bottleneck of this algorithm here. So at the worst case, it could take you around n steps. And even with binary search, even if you sort this, because you have to insert the element itself. You can't just find the index and call it a day. You have to physically insert the 2 inside this list over here. So that's why it still takes around n steps. So all in all, since we have a recursive call for the first, everything except the last element, the analysis is kind of the same. So it's the sum of 1 until n, which is still quadratic. So this algorithm, where you insert the last element, is, well, insertion sort. So both selection sort and insertion sort are pretty slow. So can we do even better? Well, since we went over Thanos search in the first half of this lecture, why don't we also try it for this particular problem? Okay, so, well, we want to do something that involves splitting something in half. So let's try splitting the sequence in half. So we have 3, 1, 4, 2. Let's split it into 3, 1 and 4, 2. And let's say we recursively sort each part. So this is nothing new to us. Let's say we now have 1 and 3 and 2 and 4. And remember, what we want to get out of this is 1, 2, 3, 4. So how do we get 1, 2, 3, 4 out of 1, 3 and 2, 4? So we have to somehow combine two sorted sequences into a single sorted sequence. So how do we do that? This is usually what we call merging. So we merge these two smaller sorted sequences into a larger sorted sequence. Okay, so for this, what we can do is, well, let's look at this recursive part first. For the recursive part, yung base case of that recursion is just an element with a sequence with a single element, which is, well, already sorted, of course. So for this, if it's already less than or equal to 1, the length is at most 1. Just return the sequence itself. Otherwise, you do the recursion, and you somehow have to merge the left half and the right half. So how do we implement merge? So the key idea here is to build up this final sequence over here. We only have to consider two elements at a time. And that is the first element of each sequence here. So let's say you have 1, 3, and 2, 4. What you can do is compare the 1 and the 2 first. 1 is smaller than 2, so you put 1 in front. So that leaves you with 3 in the first array and 2, 4 in the second array. So now you compare the first element of this, 3, with the first element of this, 2. 2 is smaller than 3, so that's the next element that comes here. So you now remove that here. So what you're left with is 3 and 4. So 3 is obviously less than 4, so you put 3 next, then you put 4 next. So the final answer here is 1, 2, 3, 4. So that's the key idea here. So at each point in time, you only need to consider two candidates. And because of that, if you do something like index-based recursion or something similar, let's say something like this is using a while loop, you're keeping track of the first element or first index of both halves. Then you build up your sequence here using those markers over here. So this is how you can implement your merge operation quickly. So how fast is this thing over here? Well, if you think about it, the key idea here is that each element here, each element in each sequence is only considered at most once. Once we're done considering it, that means it's already in the final answer. So we consider each element of each sequence at most once. Therefore, in that case, what we have here is this merge operation actually only takes us around O of n time, so linear. So all in all, what we have here is we have a recursive function, yung sorting operation, that divides its input into two different halves. So, and in order to combine those answers, it takes an extra O of n step. If that sounds familiar, that's exactly what we did over here for the subarray sum problem. We have some input, we divide that into two smaller instances, then we have an extra step that takes us O of n time. So that is what's happening if we sort like this. And we already know that if we have an algorithm that looks like this, yung running time niya is going to be O of n log n, which is why all of this takes O of n log n. And as you can see, this is much better than O of n squared. So now we have a fast sorting algorithm. And since we're using a merge operation in this algorithm, this is what we call merge sort. So this is one of the faster sorting algorithms. Okay, so this isn't all of them. There are a lot more sorting algorithms. So for example, there's heap sort, which takes roughly the same amount of time as merge sort. There's tree sort, which is also fast. Shell sort, which is kind of a bit slower. There's bubble sort, which also takes quadratic time, like selection and insertion sort. There's quick sort, which is a very good name, which, well, as the name suggests, it's pretty quick. So at the average case, it's n log n. Worst case, it's n squared. So actually, it's actually not that quick. But yeah, it can be fast if you have the right input. There's also BOGO sort, which is a pretty funny kind of sort. You should look this up. You should look this up if you want. This takes O of n times n factorial time. So that's, you already know that factorial goes very quickly. So let's say we define factorial here. Return 1 if n is equal to 0, else n times fac of n minus 1. So let's say we have 10 times factorial of 10. This already takes 36 million. So it's already getting quite close. If you have 20 times factorial of 20, this is already way too big. So this grows really quickly. So it's bad. And actually, in the worst case, this takes forever. So don't do this. You can search this up if you want to see what it actually does. But don't use it if you actually want to sort something. Okay, so you can see more of these sorting algorithms in the Wikipedia page over here. Okay, so back to our original question. What does Python's sorted function use? Well, actually, it uses a special kind of sort called timsort. So this is named after one of Python's developers themselves. And yeah, at a high level, it's a mix of merge sort and insertion sort. And there are some optimizations that use the best of both worlds here. So this is timsort. And actually, this is n log n. So now, this has actually been replaced with power sort. So this is mainly an improvement of timsort. It's still n log n, of course, but for many kinds of inputs, it's a lot faster. So this is what Python uses now. Actually, you can look up the discussion for this. And yeah, Python's implementation is actually on GitHub. The way people made Python as a language is available in the web. So you can look at this link over here to see that the same person who made timsort also made the main suggestions and implementation for power sort over here. Okay, so everything that we've been doing here, the Thanos search related stuff, as I mentioned, this is what we call divide and conquer. You divide your instance into smaller pieces, then you conquer each of those smaller pieces, then you finally combine all of them into your final answer. Okay, so this is really just wishful thinking again, except we're doing it systematically. So divide, conquer, and combine. Okay, so for more of divide and conquer, that will be coming in some of the later CS courses. For CS 11, this is as far as we will go. The main idea is you have a problem, divide it into smaller problems, solve each smaller problem, then combine everything at the end. Okay? That's divide and conquer. And yeah, that is going to be the end of this lecture here. For the next lecture, we're going to look at one of the last few main algorithms or algorithmic ideas that we'll be using for CS11, and that's memoization. Okay, so that's going to be it for lecture 20. Thank you for watching.